this is the hydrologic cycle, right? After all, it is called Waterhackweek. And one of the things that's interesting when you actually look at hydrology is just the kind of enormous variety of type of measurements and data and information that go into this, right? We have atmospheric data, which may be either observed or from a model. It's typically a time series, and it can be a time series at a single location, or it can quickly become a large spatial data set that either comes from remote sensing or is model output, right? If you're somebody who actually looks at climate change, for example, or the climate change effects on hydrology, you will often find that those data sets can grow pretty quickly. These days, you know, for a climate change study, really the recommended way is not to use a single climate model, but to use an ensemble of climate change models. And so quickly you end up with data sets that nowadays can be in the petabyte range, right? So 1,000 terabytes. And that can be really hard to handle. On the other opposite, you have kind of like single station observations that may be hard to handle for their own reason, in that they're missing data, you have data quality issues, and so on. And then in addition to this time series data, you also have a lot of just spatial data that is terrain information, right? You have watershed boundaries, you have land use change maps. Some of these are gridded data, meaning that they're on a regularly organized spatial grid. Other ones may be on irregular grids, and other ones may be just vector data, right? So in hydrology, we just have this enormous variety in the type of data that we handle. And it's not just the type of data, but it's also the source where they come from, the metadata that they're accompanied by. Variable naming is often very different in these data sets, right? So managing this data actually ends up being a very large task in itself. When I was doing my own PhD in the 90s, for a long time, my impression was that the main thing hydrologists did was transforming data from one format to another. Because at the time, that seemed to be where I was spending most of my time, basically writing little C programs or little shell scripts to take ASCII data and, you know, swap the columns or something like that. Fortunately, that has become a lot easier because, you know, Python, for example, offers a really great set of tools to handle a lot of this. But it's still typically a large part of every project that you end up doing is kind of managing this data, massaging it, getting it in the format that you need for the next step in your analysis process, right? So as I said already, data in hydrology, right, really comes from, in many forms, from many sources. And let's look at some examples, right? So one example is, for example, point time series of environmental observations. And again, there's not like one format or one source of this type of observations, right? You have things like here on the left, which is a flux tower, right? So these are towers that are typically installed at a height so that they actually tower above the canopy. And so if you have a high canopy, these towers can actually be really substantial affairs. And so this is a tower that's part of the Ameriflux network. And so they're basically installed in a wide range of environments. These are walk-up towers. Some of them are much smaller and you just can climb up them. And if it's over grassland, they may just be like, you know, a few meters high. But this is actually a large tower that has been erected. And typically they take many different type of measurements along this tower, right? CO2 measurements, temperature, humidity, radiation. There may be like short episodic measurement campaigns to measure something very specifically. But like this tower alone will be the source of many different types of data. Another example is a rain gauge, right? This is actually a USGS photo. So this is a rain gauge with a shield around it. So this is a snow shield, right? So in snow environments where you typically end up with fairly deep snowpack, the rain gauge itself is raised. And then you have a ring around it with these vanes that actually kind of influence the wind field, so you don't have too much undercatch, because otherwise you have the problem that snow blows over the gauge. So again, like what this kind of demonstrates is with observations are all kind of different and they have their own characteristics. You'll have missing data. Here on the right, we have a a stream gauge. Right, so this is also a USGS. This is actually just the part where they transmit the data. So this is like automated data that's almost available in real time. You can actually go to the USGS site and find the data that is taken at these locations. Oops, wrong channel. And then this is actually a really different time series. This is a time series where people actually take pictures. This was made by Jessica Lundquist's group in our department. They take pictures of the canopy cover to see when there is snow in the canopy and when there's not. And then they actually give that to a citizen science project to actually interpret these images and to flag the images that have snow and snow or not. And so you actually end up with a binary time series that just said yes, no, yes, no, yes, no, you know, for whether there is snow or not in the canopy. So the advantage, of course, of these type of measurements is that they're actually measurements in the real world, right? They're not like model output and so on, but they have their own challenges. Representativeness, how representative is a single measurement of like a larger area. Every measurement is associated with some measurement error. If you have real measurements, there are always missing data because, you know, technology does fail us once in a while. Often there are changes in technique. For example, they update a gauge or they have to move the gauge and you have a change in location, which affects the time series that comes out of these products. Record length may be not long enough for what you actually want to do. If you want to do time, trend analysis and time series, you typically need a certain minimal length. And then data format is often different among all these various observations, right? We've gotten much better in hydrology and standardizing how we organize our data, but there's still a long way to go, I would say. Spatial data is another example, right, of data sources. We have spatial data from remote sensing platforms. For example, here on the left side, it's actually not directly a remote sensing measurement, but it's a product, right? They take a series of remote sensing images, interpret that, and then turn that into a land cover classification. The advantage of remote sensing data, of course, is that it's typically available over wide areas. For example, you can get global products like this, and that they, you know, you don't actually have to be on the ground to make these measurements. Here on the bottom, we have another example, which is MODIS snow cover product from January 2020. MODIS is one of the NASA satellites. And then we, of course, you know, we have things like Doppler radar. And these are actually just the radar echoes. The challenge here, for example, is then converting that into an actual rain rate, right? And that has problems or challenges with it, depending on the type of rain it is and so on. So the challenges here are, again, very much the same as in for the point observations, but in addition, you have some new ones. Like data size can be a real issue, just meaning that it can be really challenging once you start working with a time series of remote sensing images. The data size can become very large very quick. The projection, meaning like how you actually map the data that's on a sphere onto a flat surface, may actually be different. And so lining up or co-registering different images can be challenging, and so on. And there's many different spatial aggregation. And then not all spatial data is gridded, right? These examples I showed on the previous page, they in some ways are easier to manage because the data is on a regularly spatial grid in whatever projection it is. But not all that data is gridded. An example for that is this USGS watershed boundary data set, right? Watershed boundaries or any line features don't necessarily follow a grid. Actually, they not only not necessarily, they rarely follow a grid, unless you maybe look at a street pattern. And so managing this data can be challenging too, right? How do you combine that? How do you take a vector data set like this to cut out a certain region out of a gridded data set, right? And so this is just on the right-hand side, an explanation how the HUCs work, right? The hydrologic unit codes are a USGS way of actually numbering all the watersheds in the United States, and it's higher the number, or the longer the number, I should say, the more digits in the number, the smaller the watersheds. And it's kind of a logical progression from very large watersheds, or like, for example, we're in Northwest, which is region 17 in a HUC, and then you can kind of subset into that for sub-watersheds. All right, so far we've basically been talking about measured or derived products and so on. One other thing that we use a lot in hydrology is model output, right? And that also comes in many different shapes. Shapes and forms do overlap with the shapes and forms of data from observations. And so a lot of the techniques that you can use to manipulate observations, you can also use to manipulate model output. Here on the left-hand side, as an example, this is a gridded data set of modeled water table depth from ParFlow, which is a groundwater model that in this case, they ran over a large part of the United States at like a kilometer resolution. And obviously it provides you with very pretty images. The question then is like, okay, since it's model output, how well does that image actually reflect what goes on in the real world? But model data doesn't necessarily just come in large gridded field, right? Here on the bottom side is a project that one of my own students worked on, and it's actually looking at climate change in the Columbia. And what we end up with is a series of line graphs. But the source of this is actually model output that's gridded over the entire Columbia River Basin, which we then reduce and distill into a set of line graphs that we can actually use to show our stakeholders to demonstrate what we expect will happen within the Columbia River Basin under climate change. And then one of the things that will happen is that stream flow will shift timing because of less snow by the end of the century. And then you have other things, like here on the top right-hand side, it's actually modeling a snowpack, but modeling a snowpack in many different layers. And these plots actually show you a slice through the snowpack over time and show you different characteristics of that snowpack. Basically, it shows you like the depth of the snowpack, but then on the left-hand side, the temperature within the snowpack, the volumetric water fraction, and conductive heat flux. So model output does have certain advantages, right? There's typically no missing values, which makes it, which can be really challenging to deal with in an observation data set. It can provide you insight into variables that cannot be measured easily or at all. For example, the conductive heat flux in the snowpack, which is the figure on the top right-hand corner, is something that would be really challenging to measure in that much detail within a snowpack. Right? And so it can also provide you insight into conditions that do not exist or do not exist yet. You can play what if scenarios. So for example, on the bottom left-hand side, you can look at like what would climate change effects be within on the hydrology of a specific river basin. So there's really good reasons to use models, but models of course come with their own challenges. You have model error, model uncertainty, and then again, just dealing with it in the sense of data format, data size, many different spatial arrangements and so on, can make this challenging, right? All right. So that's the kind of different types of data, right? Let's talk a little bit about data discovery. One of the things that you probably already started with yesterday and probably will continue with today is kind of wondering like, okay, where do I actually find the data that I need for a specific project? And the challenge in hydrology, and probably not just hydrology, is that data tends to be scattered across many different sites, repositories, and so on, and may be difficult to locate at times. Sometimes it's sitting on somebody's hard drive that you do not have access to, or it may be offered under a license that doesn't make it available to you in an easy way, right? One reason that a lot of hydrology studies in the scientific literature are done in the United States is that actually hydrology data and meteorological data in particular are freely available. And that's not actually true in a lot of the countries or a lot of geographic regions around the world. So in that sense, we're actually in a pretty good situation here in the US. USGS stream flow data, you don't have to pay for any of the NOAA weather station data and so on. It's freely available. And actually a lot of our remote sensing data is freely available. Now there's of course remote sensing products that you have to pay for or that we may never get our hands on because they're classified, but there is a lot of data available. And so data discovery remains a challenge just because data is in so many different places. It's all kind of different formats, different metadata and so on. But there are initiatives to make this easier. So where can you find data that you might need, right? As I said, there's unlikely to be a single catalog that meets all your needs in all domains of water research. You may be lucky that for your specific project, there's one single location, but as soon as a project gets fairly involved, there's likely to be many different places where you need to start looking for this. So what are some possible starting points, right? When you want to start looking at data? Well, obviously Google search, I mean, like, you know, that's typically what my starting point would be, or, you know, you can use another search engine. The Google is just search engine search, let's say that way. The problem is that if you search Streamflow US, you may get, well, luckily in that case, probably the USGS will be your first hit, but there might be many different hits that you get. And it can be really overwhelming, and there are many irrelevant results that you get out of this. If you want to look specifically at spatial data, and very much so remote sensing data, Google Earth Engine may be a really good place to start, right? Google actually has invested money in basically assembling a very large remote sensing archive that is very easily searchable. You can look for whether images were taken on a certain date and so on. Now, if your particular product is not indexed, or the data that you're interested in is not indexed or is not present in Earth Engine, then you're kind of out of luck. And they do now have some model data in there as well, but not a whole lot yet. So it's fantastic for remote sensing and data and processing. You can actually do the processing right there in Google Earth Engine. And Python is actually one of the way you can do it. The other one is JavaScript. It's not really there for site time series. So if you wanted a single rain gauge, that's typically not available. And then there's actually also a Google dataset search, which is kind of a new product. I would say results are mixed. But so these are kind of like general purpose starting points. As soon as you end up needing very site-specific data from a very specific source, you're unlikely to find it in these latter two. It may or may not come up in your Google search. So there's also a lot of topical or organizational repositories. Sorry, repos in this case is just repositories of data. So, for example, in the US, a great source is the USGS, right? The USGS is kind of in charge of collecting streamflow data, but it also organizes a lot of our other water data. And so the USGS has an archive. You go waterdata.us.gov, and they have lots of things, from current conditions to like historic data and so on. Similarly, NOAA, the National Climatic Data Center, NCDC, stores a lot of information. Of course, it being NOAA, they focus more on the atmospheric side. And it's a very good place to start. But you can already see right now, you really have to kind of like know already where some of this data will be available. Washington State, for example, also has its own Washington State Geospatial Open Data archive or portal. And you can go there, and it has a lot of data if you're particularly interested in Washington State. Now, if you're interested in Idaho, it will be a different place. They're probably not organized the same way. Their interface with interacting with the data is likely to be different. And if you want to do a project that actually covers the Pacific Northwest, it may actually become rather hard to kind of combine all that data, find it, and put it back together in a seamless map and so on. So it's great that this data is there, but depending on what you need to do, the data managing often remains a very large part of your project. And then, for example, Kawasi, who is co-sponsoring this Waterhackweek, and you've already met some of the people from there, like John Pollock and Tony Castronova. They actually also have tools that allow you to do data discovery and analysis. And it will be very good to go on there. It's interesting because their data sets often are quite different from the ones in the other repos. And HydroShare, of course, allows you as a researcher to share your own data with other people. One of the requirements to make that data useful for other people is actually being very clear on what the data is, how it was acquired, so metadata, and how it's organized. So metadata and documentation are incredibly important if you actually want to share your data with others. All right, so let's assume that you actually were able to find the data that you need, and it's very likely that it isn't in one of the repositories that I just mentioned, right? It may be that you finally found that colleague down the hall who has been collecting rain gauge data in a coffee can that is the exact data and location that you want and he has it on a old floppy drive somewhere in the back of his cabinet. So there's still many different ways to actually find this data. And often the problem looks like this, right? This is what do you call it? A cartoon from XKCD, which is generally pretty funny. And so in this case, he's kind of pointing out the universal converter box, which changes all these different cables that we have. And I'm sure that if you look around your desk, you probably have 10 cables lying around to connect your phone to your whatever, right? So here we have, on the left-hand side to a gas pump on the right-hand side. And hydrology, to me, often feels like this. Like, with that universal converter box doesn't really exist, although, as I said, we're getting much better towards actually having tools in, for example, Python that make this possible. But it's basically, the data was provided me to the format to the left-hand side for my analysis, or to create model input. I have to have the data in the format on the right-hand side. And now I have to do this conversion, right? So once you find the right data, accessing it, manipulating it, and so on, is a very significant task in many cases. And fortunately, there is a large set. It doesn't mean it will do everything you need it to, but it should make it a lot easier. And in the following 3 presentations, you'll actually see some examples of this. All right, so data access and ingest, right? So there's a lot of ways to actually kind of approach this and tools, right? So manual browsing for the data, downloading it, and then reading the files locally is still something that we often do, right? The challenge with that is often that it may not be easily reproducible, because if you're doing this and reading it into an Excel spreadsheet, and then you do manipulations in an Excel spreadsheet, it's really hard to kind of just tell people what you exactly did and how you change things. It can also be inefficient if you have to do this many, many times, right? So there are different Python packages to actually download data. There's a requests package that allows you to do remote access through the web. Pandas, which is a package that I'll talk about a little bit later, and which will be extensively used in the rest of the tutorials, is a package that basically is really optimized for analyzing time series data at a single location. And that, for example, has a large set of access methods. One of those is read CSV, so a comma separated values. So, and it can actually files that are not just local, but you can actually directly access remote files. Like, so without having to first download them and then doing something, you can do that all in one call. There's custom web APIs. APIs are called application programming interfaces, and they're basically codified ways for accessing data remotely. And then there are actually standards-based resources that actually allow you to do this. So OpenDAP is a way to basically access data remotely. And for example, if it's gridded data, you can subset it. You can sometimes do operations on it. There are formats like WaterML. If this doesn't mean a whole lot to you, don't worry. We'll come back to these in the rest of the tutorials. NetCDF is a way to organize, in particular, gridded data, but you can also use it for time series data. And the advantage of NetCDF is that the metadata is actually embedded in the file itself. And then Quasi has a bunch of standards and so on. And standards are really important, right? If you have to figure out what format you're going to use, using some standard really enables reusability across people and multiple data sources and systems. And then there's actually a dedicated Python package to access water and climate data, which is called ULMO, which we'll actually see later. All right, data storage is another issue with data, right? One of the challenges is that data storage is pretty cheap, we say these days, right? Like having a terabyte disk isn't that much of a challenge. But data volumes can actually become very large, very, very quickly, especially if you're dealing with large gridded model output or remote sensing data. For example, exactly what I said. In addition, storing your data on a local hard drive without a backup is, I would say, more than risky, right? Like, disk failures happen all the time, and just keeping your fingers crossed isn't really the proper way to be managing your data that it took you a long time to either collect or manipulate or analyze and so on. So in addition, downloading data locally from an archive can actually take a long time when volumes are large, right? I mean, downloading a 100 megabyte file isn't really an issue. downloading a 1 terabyte data set, especially now that we're all working at home and don't necessarily have access to our university networks, can actually take an enormous amount of time. And so for very large data set, the paradigm these days is take the computing to the data. And one example of that is, for example, Google Earth Engine, where you actually, the data is stored at Google, and then you actually do the computation in the cloud to access that data directly. There's no data download involved. And, in some ways, we'll see some of that later during the tutorials as well, since you'll be doing the computations in the cloud. In that case, it's not so much because of the data volumes. All right. Some other examples are Pangeo, and HydroShare also offers you some opportunities. All right, data publishing, right? So say you have a data set, or you have, say you have a data set that can be either observation-based or model-based, and you now want to share that with other people, right? Say you have a paper written about this. And so one of the reasons is, why would you want to do this, right? Well, one really good reason is that most of the journals, or a lot of journals, when you publish a paper these days, they also expect you to publish the data that's associated with that paper. So AGU basically had, the American Geophysical Union, which is a kind of the home professional environment for a lot of us, but like, ASCE and so on have similar ideas. So AGU basically says that Earth and space data science data should be widely accessible in multiple formats. A long-term preservation of data is an integral responsibility of scientists and sponsoring institutions. All data necessary to understand, evaluate, replicate, and build upon the reported research must be made available and accessible whenever possible. And actually, some journals are more stricter than the whenever possible. They will actually not take your paper if you're not willing to share the underlying data. AGU encourages authors to identify and archive their data in approved data centers. And approved data centers are the ones that actually will enable long-term storage of your data, right? So it doesn't die, the data doesn't die when you move on and your hard drive fails. And so there are actually standards for doing this data publishing as well. One of them is called FAIR. Well, actually, it's not a standard, but it's basically an initiative to make data findable, accessible, interoperable, and reusable. And so in Earth Sciences, there's a greater and greater kind of urge to kind of follow these principles. They were basically originally made to make data-driven and machine-assisted open science more easily possible, right? Because like your machine needs to be able to, if you're doing a large machine learning project, you want this data to be in an easy to read format. It's not, FAIR itself is not the same as open data. You can have your data be findable, accessible, interoperable, reusable without it necessarily having it openly available. But this is something that people really want to, that a lot of organizations pushing for really hard. So where do you actually publish your data? So publishing the data really means that you publish a frozen set of your data that doesn't get modified after you publish it, right? If you want to publish an update, you publish that separately as an update to the initial data set, so that when people access a certain version of that data set, they're guaranteed to get the same version. And one way to do that is actually to make sure that you get a DOI, a digital object identifier for a data set. And the advantage of that is also that they can then track how many times your data set was accessed, for example. So HydroShare actually has a mechanism for doing this, to permanently publish your data set. And as they point out, once published, you can no longer change a resource's content or metadata description. So sharing data on HydroShare is not the same as publishing that data, right? You can make it publicly available, but publishing really means that you freeze the version. All right, Zenodo is actually a European archive, but it works very similarly in that sense. All right, my last slide, because I'm out of time too. I have 1 minute, so perfectly on time. The Python ecosystem, right? So, and there's nothing really particular about us using Python, right? We use Python because it has become kind of a de facto, I wouldn't say standard, but it has become kind of a really widely used tool within Earth Science. Other people use R, and I think R, like if that is your language of choice, that's great too. R is kind of very similar in that it has like a huge range of add-ons and packages and so on that you can use to do most of the same things as you can do in Python. So I would say those are probably the two big free ones. MATLAB would be the other one, but it's not free. And I would say like that the other two are very quickly eclipsing MATLAB in certain areas with the libraries that they have available. Obviously in industry, MATLAB is probably still the larger one because of the, you can pay for support and so on. Okay, so the Python ecosystem that we'll be using. NumPy is basically the mathematic or the numerical library within Python that kind of underlies a whole bunch of these other packages that we use. Matplotlib is a plotting library that we'll use. Pandas is kind of built on top of both Matplotlib and NumPy and is really optimized to handle time series and manipulate time series. And so you can very quickly read in data, calculate averages. Xarray is kind of built on top of these three and actually helps you manage gridded data. And Bokeh is actually just another plotting library. I don't know if we actually get into this today, but I'm just saying Matplotlib isn't the only one. Bokeh is really nice if you want to make interactive graphics. Cartopy or Cartopy is a mapping library, so you can actually spatially display your data, for example, on a map. Rasterio allows you access to geospatial data. Ulmo allows you to directly access and find time series data on the web in the hydrology domain. And then Jupyter is actually it's written in Python, but it's actually an environment that it allows you to interact with your data on the fly. And we'll actually use that in the following 3 tutorials. Here's some more information. There's some other learning resources that we have. There were a bunch of cyber seminars that have covered the same set of topics. And then, of course, there's a GitHub repo. And with that, I'll end